This is AP Chemistry Unit 8, Equilibrium. These are the topics for today. First is the dynamic equilibrium. And there are two main types of reactions, which are reversible and irreversible reactions. So reversible reactions are literally the reactions that can be reversed, so it can go both ways. And irreversible completion reactions are the reactions that only go one way, so products cannot become reactants, while reactants will become products. And for example, there's dissociation of strong acids or bases that go to the completion. So most reactions do not go to completion, so they are reversible. And dynamic equilibrium is when the system reaches a dynamic state where reactants are continuously becoming products and products are continuously becoming reactants. And at equilibrium, if you look at this graph, from this time on, the concentrations of reactants and products will not change, so they'll stay constant. And that is because products are continuously becoming reactants at the same rate as the reactants are continuously becoming products. So the forward rate, which removes the reactants, is equal to the reverse rate, which removes the products. And these graphs are only possible in closed systems where everything happens perfectly in chemical terms. So at equilibrium, concentration of reactants and products are constant because forward rate equals the reverse rate. Next topic is the Keq and Kp equilibrium constant. And for this particular reaction, Keq equals concentration of reactants, so concentration of C to the C power, the coefficient, times the concentration of D to the D power, over concentration of A to the A power, the coefficient, times the concentration of B to the B power. And the pressure equilibrium constant is written in the same way, but it is for the partial pressure for each species. And this is very important that solids and liquids like H2O are left out of expression. So even though you have, for example, H2O in the equation, you have to ignore it and not include this in your equilibrium constant expression. And you can calculate Kp or Kc if you only know one of them with this formula. Kp equals Kc times RT to the delta N. And delta N is the number of moles of gas products minus number of moles of reactant products. So for example, for this equation, delta N would be 2 minus 1 plus 3, 4. So negative 2. Because there are 2 moles of gas products and 4 moles of gas reactants in total. Also, there are 3 cases for Keq. So if Keq is larger than 1, there will be mostly products at equilibrium, and equilibrium lies far to right. And you can derive this from this equilibrium expression. So if Keq is larger than 1, from this expression, it would mean that the numerator is larger than the denominator, because Keq has to be greater than 1. And because the numerator, which are products, are larger, it means that at equilibrium, there will be mostly products. And if Keq equals 1, it means there are equal amounts of reactants and products because numerator has to equal denominator. But if when Keq is less than 1, it means that the reactants, the denominator, is greater than the product's numerator. So it means that equilibrium lies far to left. And we have an example question here. Write the equilibrium constant expression. So Keq, also represented by Kc, they mean the same thing, equals the concentration of product, ammonia, squared, because of this coefficient of 2, over the concentration of N2 times concentration of H2 cubed, because it has a coefficient of 3. In the same manner, Kp would equal pressure of NH3 squared over partial pressure of N2 times partial pressure of H2 cubed. These will be your equilibrium constant expressions. The next topic we are going over is the ice chart, and it is very important that you will have to use this a lot when you're solving questions for equilibrium unit. So it says you start with water and its initial partial pressure is 0.784 atm and its Kp value is 2.0 E negative 42. Calculate the partial pressures of each species at equilibrium. So first you have to set up the ice chart, initial, change, and equilibrium, and you write the equation of water decomposition. And it says the initial partial pressure of water was 0.784 atm and 0 for both products. And for change would have to be negative 2x for H2O because it is the reactant and it has a coefficient of 2, plus 2x for H2 and plus x for O2. And then at equilibrium, the partial pressure of H2O would be the sum of these, which is 0.784 minus 2x and 2x and x for O2. In order to find these, you'll have to set up the equation of Kp and then plug these terms in. So as we just learned, Kp will equal the partial pressure of H2 squared because of this coefficient times partial pressure of O2 over the partial pressure of H2O squared. So we have these terms, so we just plug these in, which is 2x squared times x over 0.784 minus 2x squared. And then the question gave you the Kp value, which is 2.0 E negative 42, and then that equals this expression right here. And you simplify this, 2x squared is 4x squared, and that times x is 4x cubed over 0.784 minus 2x squared. And then now you have to solve for x, but if you look at the question here, it says Kp value is very small because it has a very large negative exponent. Because the Kp value is very small, it means that reactants are favored at equilibrium, so there will be mostly reactants at equilibrium. So products will not be that much at equilibrium. So x value will be very small. And because x value is very small, we can just simply eliminate or ignore this x value, and we can just think of it as 0.784 squared. Then it will be much easier for you guys to solve for x. Equals 4x squared over 0.784 squared, and you solve for x, which you get 6.7 E negative 15. And then with this x value you just calculated, you can get these partial pressures of each species. So therefore, partial pressure of water will be 0.784 minus 2 times x, which equals 0.784. And you see that the value did not change because x value was very small, that it was negligible. So you now see that it was fair for us to simply just ignore this x value in the denominator. And for hydrogen, it will be 2x, so 2 times 6.7 E negative 15, which you get 1.3 E negative 14. And you cannot forget the unit, which is atm. And lastly, for oxygen, it equals the value of x, so it will simply be 6.7 E negative 15 atm. And these will be your final answers.